Yeah, you ready?
Hello, everyone, and welcome to this episode of the YoungWonks podcast. Today, we're talking about speeding up your Python programs. Got a lot of other stuff open right now that's not related. Hang on. Okay. What we are going to talk about is, first of all, why this is a problem. So you see, Python is an interpreted language, which means that rather than being turned into instructions that run directly on the processor of your computer, Python has a program called the Python interpreter that looks through your program line by line and does what it says. So there's a lot of basically interpreting involved in this, i.e. it has to take the code, break it up into tokens, work out what you're trying to do, and then do that. What a compiled language does, it takes the code and does all that beforehand and spits out machine code, which is the actual instructions that run directly on your computer's CPU. Now, how do you speed up your Python programs? Basically, you need to get around the fact that Python is an interpreted language. You have to do something that is faster than interpreted. So, what are the available things? The first one we're going to talk about is, I think, one of the oldest, and it's called PyPy. PyPy is an alternative interpreter for Python that uses just-in-time compilation, or JIT, J-I-T, in order to basically compile your program as it's running. So if you had a program that basically runs through just once, it doesn't really help you because it's compiling as it goes, and there's some overhead associated with that. But maybe you've got a loop in your program that runs 100,000 times, or maybe 1,000,000 times, 20 million times. I don't know. It's some calculation loop that runs many, many times. You could benefit from something like a JIT because it's going to actually take that loop and turn it into optimized machine code that just runs directly on the processor, so it doesn't have to interpret the code each time. So let's do some super basic tests and just show how this would work. You're going to install PyPy using something like, apt install PyPy 3. You're going to download it on Windows. Make sure you get PyPy 3 so that it's Python 3 compatible language-wise. Now, let's just look at something like, some kind of calculation, something that'll take a while that could benefit from this. One of the slowest things in interpreted languages like Python, especially, is looping, because there's just a lot of overhead associated with it. So let's make a loop that sums up the numbers from, 1 to 1,000,000,000. Import times, let's go create a function, start equals time.time, sum, or let's go s equals 0, for I in range 1, 2, 3, 4, 5, 6, 7, 8, 9, 1 billion, s plus equals I, print s, end equals time.time, print end minus start. Okay, so this gets the current time loosely, and then it sums up the numbers from 1 to 1,000,000,000, prints out the sum, gets the end time. Don't know how long this will take to run. If it takes too long, maybe we'll do more like 1,000,000. But let's run the function and see. Do bum bim 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 bum bim ba bing bong bing bing bing. If this just doesn't, end ever, then I probably picked a task too large. In a compiled language, summing stuff from 1 to 1,000,000,000, you could, if it was integer numbers, you could do probably like just a few CPU instructions per iteration of the loop. But I think in Python like this, it's going to take really a very long time, so I think I might want to actually choose a smaller task. Sorry, let's try that out. Let's create the function again. Time.time, s equals 0, for I in range 1, 2, 3, 4, 5, 6, s plus equals I, print s, end equals time.time, print end minus start, f. Alright, so that's the sum, and it took 0.07 seconds to sum the numbers from 1 to 1,000,000 using the most inefficient way possible. Obviously, those of us who know math could find easier ways to sum the numbers from 1 to 1,000,000, but I just wanted a task that would really burn some time. So now let's try it in PyPy. Now, I don't know if this is a task big enough for the optimization to actually show, but let's see. Import time, def f. By the way, you notice in Python the prompt is 3 greater than signs, but in PyPy it's 4. That's just to show you that you're in PyPy. So let's make a task. Time.time. S equals 0. For I in range 1 million. S plus equals I. Print S. End equals time.time. Print end minus start. 0.004 seconds versus 0.07 with regular Python. This is a serious improvement. In fact, regular Python is, for this specific task, 19 times slower. Yeah. PyPy is an amazing technology, and if you've got a Python program that you just want to go, you know, from slow to fast quickly without a lot of rewriting or refactoring or anything like that, very often it'll get you there. Now, disadvantages with PyPy. Libraries, sometimes you don't have them. Sometimes libraries don't work with it. It doesn't really have the same API for attaching libraries as Python, at least not exactly the same. So stuff has to be recompiled to work with it sometimes. I think NumPy used to have issues. I don't even have NumPy installed for PyPy here. If you're doing something with NumPy, I would actually suggest you use Numba. Now, Numba is a Python compiler. It is honestly in many ways similar to PyPy, but it's I believe it can compile like an entire thing at once instead of doing it as JIT, although it also does JIT it. It's also more focused on numerical computing. So if you've ever used the NumPy library for like scientific stuff, data analysis, and you found that, you know, some of your stuff was slow and you wanted to speed that up, I would recommend using Numba instead of PyPy. PyPy has always been a little bit dodgy with NumPy. PyPy, I remember, being this JIT that we just tried out that speeds up arbitrary Python programs. So I'm going to get out of PyPy here. Now, the other thing Numba does, and this is really interesting, is it'll also generate vector instructions. So on a lot of modern CPUs, there are these special instructions to the CPU that actually work with multiple pieces of data at once. They're called vector instructions. Vector as in, you know, like multiple numbers, not vector as in like direction and magnitude, really. Although, you know, you could be calculating with vectors. But these vector instructions can operate with multiple pieces of data at once. They're often used to optimize things. Numba advertises that they will generate instructions for the CPU that take advantage of this feature. Additionally, they can generate CUDA or ROCm code. So CUDA and ROCm are AMD and NVIDIA's APIs that allow you to run arbitrary code on their GPUs. We'll talk about this a lot, probably in a future episode, but a GPU you can think of as like 1,000 very small processors all in parallel. GPUs are designed this way because graphics processing is a very parallel task. But what it means in practice is that if you can run arbitrary code on a GPU, you can speed stuff up a lot. Opencl is the sort of open API for doing stuff like this. CUDA and ROCm are the somewhat proprietary ones from the GPU manufacturers themselves. ROCm is kind of sort of open source in some respects, kind of. CUDA is completely closed source. CUDA is used a lot for professional AI stuff, because if you're doing high performance computing for AI, you're pretty much always on NVIDIA GPUs these days. Yeah, they've got quite a bit of support. Numba has gotten a lot better over time. I looked at it about 5 years ago and it was pretty bad in terms of what it could do, but they've really pulled it together. Now, but before we even dig into that, there's the elephant in the room that has to be addressed. The true way to make your Python programs fast, the hard way. Don't write them in Python. What do I mean? You need to take the performance heavy, the performance critical parts of your Python program and write them in something like C or C++. And then you can have your Python program call those functions. So how do you do that? How do you get C functions to be accessible from Python? There's obviously something that Python does a lot. I mean, A library like NumPy or SciPy or OpenCV, it's all written in C or C++. But you can call the functions from Python and access it, and it'll act like, the things will act like Python objects. So how do you do this? Well, what you do is you write something called a Python extension module. So a Python extension module is a C or C++ library, the same way that a library works normally in C++. You've got some code and you compile it down to machine code in a way that the code can then be used by other things. Not going to go into detail there. But it's one that's set up so that it'll integrate with the Python interpreter, so that the interpreter can actually look through the library and find all the functions that are callable and make them accessible to Python. So how does this work? There's a few different ways to do it. Let's introduce the dumbest one first. In my opinion, this is something called C-types. So this is actually a really useful tool in certain situations. It's just performance-wise, it's not great. So what C-types is, it's a module that comes with Python that allows Python to load a C, C++ library without any modification to the library, just a regular C, C++ only library, and access it. It is generally used with C libraries, because C++ libraries have something complicated called symbol mangling. It gets tricky. But let's try it out here. So on my system, let's go into /lib, which on Linux computers has all your libraries. Let's just find any old library. Let's find the C standard library. How about that? Well, here. Where's the C standard library? Give me a moment. I have to search for it. Okay, hang on. I'm trying to find it. There we go. Okay. On my computer, the C standard library, which is basically all the functions that the C language has built in that are or is usually always accessible to you, is in a file called this, /lib/x86_64-linux-gnu/libc.so.6. It's under /lib because it's a library. This is the platform that I'm on, and then libc.so.6 is the name of the actual library, glibc, standard library. So C-types actually lets you just load this pretty much, just by itself. So I'm going to actually load the C library and then just try calling functions from it. What you do is you do something like, you're going to create a variable. I'm going to call it C library equals ctypes.cdll.load library, and then you give it the path. Now you might wonder why it's called a DLL. DLL means dynamic link library, dynamically loaded library, something like that. It's how shared libraries are done on Windows, but it's in this case just being used as a generic term meaning a library you can load while your program is running. So now we've got this object C library that we just loaded, which has access to the function. So if you look in this thing, you can actually access functions in it. So Printf is a function that many of you might have seen if you've ever programmed in C. It prints stuff out, prints stuff to the screen. So we can actually use it like this. clibrary.printf, hello world. You can see that it kind of didn't like it because it interfered with the Python interpreter, and so it only printed the H and then it got erased. So if I put a new line, yeah, it's only printing out the H, the rest of it's getting wiped out. That is a little bit tricky. Give me a sec. Yeah, it doesn't like you doing that. But you can do things like .time, which will crash the entire thing because we forgot to give it a pointer. Now this brings us to a very, very important point if you're calling C libraries from Python. C crashes are a thing. Anything that can happen in C, segmentation faults and all that crazy stuff that you've never encountered because you use Python as your main language, that will happen. If you're calling C functions, you have no guarantee of the safety that Python gives you. clibrary.time gets you the current time. So as you can see, if I keep calling that, it goes up once a second. Very nice. So you can call an unmodified, just a regular C library this way. However, C-type's performance is bad compared with writing a C or C++ extension module for Python. And also, if you're working with C++, you're going to have a really hard time with the C-types library because it's kind of hard to call stuff. So if you're somebody like the people who wrote the OpenCV library and you want to make a fast, high-quality Python binding so that Python could call your functions and use your library, you will write a Python extension module. And you can do this manually. You actually use a special library called libpython, basically, and you tell Python about all the functions that you want accessible, and you tell Python the types of data that can be passed in. It's a lot of code. It's really a lot of code you have to write. I recommend you use something called Swig. I'm trying to find my example project. Here we go, Swig example. So Swig is this really nice program that takes a C or C++ library and generates all the glue code that turns it into a Python extension module. And this is fast. This is really fast because then you're just accessing C code pretty much directly. So as you can see here, I'm going to delete the files we don't need. What you do is you've got your Python program that's going to use it, and you can actually just import the thing as if it was a regular module. But if you actually look, the way you write the module, you don't write it as a Python file. You're going to write it as a C file like this. I've got two functions here. One is called square, one is called ASCII sum. This was just a demo. And then you're also going to have a .i file. This is a Swig interface file, and it describes to Swig which functions in your C library should be accessible to Python and how they should be accessible. And by the way, you can use this with other things than Python as well. You could use this like to make a Lua library or even to bind C to Java. You can use it to create bindings for many languages. But when you run Swig, I've actually got a makefile here that runs it for me, but I'm going to do it for you here. So if you run Swig, you do swig-python-py3 example.i. You'll see it's created a file called example-wrap.c, and this file has all the crazy code you need to inform the Python interpreter that you are trying to build an extension module, and these are the functions and how they can be called. It calls a lot of these like py something functions in C, a lot of py object structures. All of these are basically stuff from the API that you use to talk to the Python interpreter to inform it of how your library works. The binding code here, just all this boilerplate stuff and the code for the two functions, or to set up those two functions to be accessible from Python, is 3,804 lines long. This is why I don't recommend you write your own or roll your own extension modules. Just use Swig to generate it. So the Swig tutorial has a pretty excellent documentation on how to do it, but make sure you use the instructions for Python 3, not Python 2. So once you have compiled your thing into a Python extension module, you can actually import it the same way you import any other Python library, and you can call functions in it. And that is really quite useful. So, would you recommend, I see questions. Can you use the C file and open it in a Python program and run it using the module? No, you have to compile C code before you load it from Python. You can't just like do import example.c and have it run the C code. You have to compile it, and it has to have all this, what I like to call glue code. It's also called binding code, which is the code that, goes between the C and the Python to link them together. It's complicated stuff to write that glue code, and so I recommend you use Swig to generate it for you. Would you recommend VS Code over Pycharm? Yeah, it's a lot lighter weight IDE. If your computer struggles to run something as big as Pycharm, then I would say maybe go with VS Code. Personally, I run Vim for everything, so I don't do that stuff. I don't use IDEs very much, but yeah, I use VS Code occasionally when I need to do git merge conflicts. What features? Pycharm is a full-featured IDE. VS Code is a text editor with some IDE-like features, so Pycharm is going to give you a lot more instrumentation and analysis of your code. but I think very often, especially if you're just starting out, it's overkill to use an IDE like of that complexity. Kind of like flying the space shuttle to get to the grocery store. There's a lot of buttons and a lot of things that you'll probably never press, and it's kind of overkill for the task. So yeah, something lightweight like VS Code is very often a good choice. Now, a C extension module, there is a little bit of overhead associated with this. This is our last thing we'll talk about. C extension modules, there's a bit of overhead basically going between Python and C, converting the data into the right forms that C can use it, and then converting the data that's coming back as return values into something that Python can use. However, if you've got big processing, I think that this is your best way of doing it. Now, there's also something called Cython, which is really interesting. Cython is like a mix of C and Python. You can mark different variables in your Python code with explicit types instead of, using the dynamic typing that Python normally has. And then Cython will compile it into something that's very close to C in speed. It's kind of like PyPy, except sometimes faster because you're actually specifying types on variables. A lot of the overhead associated with a dynamically typed language goes away. So if you need some high performance computing and you don't want to write it in C, then I recommend you do it with Cython. But remember, if you write a program with Cython, unless you actually mark all your variables using their special annotation syntax or whatever to say, this variable is an integer and will always be an integer, this is a string and will always be a string. Unless you do that, you don't get a huge amount of speed up. Most of the speed up comes from the fact that you're telling the computer more about what is going to happen with variables. With Python, if I create a variable, it has no idea what the type of the variable over its lifetime could be. If I have a variable called s that's equal to 5, I could add 3 to it, but then I could set s to a string, and that's fine. That slows down Python because it basically has to check each time, what is this variable? Can I use this in this situation? Do I need to convert it to another type? In C and in Cython, sometimes types are fixed, and that gets you quite a bit of speed up. So I would certainly recommend you look into all of these different ways of speeding up your Python programs if you find they're too slow. Although, a word of warning, if your slowdown is because you're waiting on I/O, like you're waiting for something coming over the network, or maybe you're waiting on another library, writing it with C or Cython isn't going to speed it up. It's if you've got a lot of computation, pure math, that's being done in Python, that you could get quite a speed up by moving into something that's, less interpreted. That's all I got for you today. Thank you all for coming. Thanks for more questions. Do you have to install Swig, Cython, PyPy3, and the other things? Yes, you do. They're all installed different ways. I'm on Linux, so I just did, I used the package manager, sudo apt install PyPy3. Cython you can install using pip, pip3 install Cython. It's really slow to install because it has to compile some stuff, but it will install eventually. Swig you install through the package manager, or if you're on Windows, you just download it and install it. Some of these are a bit tricky to install because they involve compiling things, but they usually hide that from you. Swig is the easiest to install because it's really just a generation tool. It doesn't actually compile anything. All it does is generate code for you. But yes, you do have to install all of these. The only thing you don't have to install is Python itself, the default Python interpret. Well, you do have to install that, but most people already have it installed if they're listening to a podcast on how to speed up their Python programs. So yeah, seeing as that's all our questions. Oh, what computer do you use? I am on, here, I'll run screen fetch. This is this cool program for Linux that gives you a dump of everything that you're that's on your computer. I am on an Intel Xeon dual socket server. I've got 24 threads, 2 CPUs, 12 cores, 6 on each CPU. It's running Debian 10 Buster with the GNOME 3 desktop. It's got a Radeon RX 580 GPU, and the CPUs are Xeon X5680s. This is about a 10-year-old computer. It's quite old. I got it because it was being recycled, but I upgraded the CPUs a bit and put a new GPU in it, and it's got 64 gigs of RAM because old RAM is really cheap on eBay, so Yeah, it's kind of a weird setup, but it works well for me for programming because a lot of cores and a lot of RAM is good if you're compiling big projects. So yeah, it's an interesting project if you can get your hands on like a 10-year-old server cheap on eBay or something, or being recycled, to try to fix it up and update everything and try to use it as your machine. Anyways, yeah, I am signing off now because we are over our time anyways. Thank you all for coming. Please come next week at the same time. We're doing more sort of programming related stuff for the next few weeks, but we'll return